Okay, so good day, viewers and students. So today, we will be discussing about shear and moment diagrams. Okay, um, I address this um, video to those who are my students under the subject mechanics of deformable bodies. But somehow, even though the one who is watching this is not my student, I am still hoping that this series of videos will help you understand better um, how to um, construct shear and moment diagrams. Okay. So when we talk about shear and moment diagrams, we talk about the we talk about the internal reactions inside a body. Okay, for this series, um, since we are still at mechanics of deformable bodies, so we concentrate on beams. Okay, so when a beam is acted by different types of of loadings. Okay, for example, this. Okay, for example, this beam is acted upon by a point load at the center. Okay, so this is its shear and moment diagrams. Your shear diagram, okay, your shear is represented by V, and your M is represented by moment. Okay, so this graph shows the changes in the shear and moment with respect uh, to the to a um, certain value of x. Okay, in which your x is any uh, is any distance from the leftmost side of your beam. Okay, so let us say you are trying to find what is the value of your shear x from the leftmost support. Okay, so by looking upon the shear and moment diagrams or graphs, you will see what is the value of your shear um, at that point. Okay, for example, this. So you will see what is the value of your shear or internal shear at that point, and also your moment. Okay, so there are actually several ways in order to construct your shear and moment diagrams, but somehow in this series we will be talking about shear and moment equations. Okay, most of our um, examples we will be talking about shear and moment equations. Okay, so shear and moment equations is actually flexible to any type of loadings. Okay, so so we will be talking about this drawing. For example, you have a point load P at the middle. Your shear and moment diagrams with your Vx and Mx diagrams respectively as follows. Okay, so here you can see that um, there is changes. Okay, so there are times along your x-axis. Okay, so this is actually the line which represents, okay, your zero value. Okay, so when it is upward from this line, your shear is more greater than zero. If it is under this line, your shear is less than zero. Also, it is true for moment. Okay, so if relative to this line, okay, in which relative to this line, okay, which is theoretically where your zero moment happens. So above this, your moment is positive. Below this, your moment is negative. Okay. So also this is true whether what type of loadings um, your beam or your simple span is experiencing. Okay, so in this series of um, videos and examples, we will be talking basically on um, simple span beams, overhang beams, and overhang beams. Okay, so here this is the shear and moment diagrams of simple spans depending on your loadings. Here, it's a point load which acts at the middle. Here, W. Okay, when we say W in this series of videos, we are talking about the distributed load. So whether your load is distributed rectangular load or triangular load, or something like um, distributed load but has a certain degree. Okay, let us say n degree. It might be third degree, second degree, or fourth degree curve. Okay, so it will have its own um, shear diagram and moment diagram. Okay, so in order to understand this better, okay, we will be discussing on how to construct your shear and moment equations. Okay. Okay. So, okay. Okay. Okay, so in constructing your shear and moment equations, um, uh, I have this okay, I will present to you a certain table. Okay, um, do not worry. Okay, because as we go on with our examples in the next series of videos, you will understand what I mean today. Okay, what I mean uh, uh, with this table. Okay, so without further ado, I will explain. Okay, so when you're okay, so here we are referring of the we are drawing a beam, okay, in which only one side is being emphasized. Okay, so let us say you have a simple span beam. Okay, we cut it into which your left supports was only left. Okay, and then there is a load acting at A, at distance A from that specific load. Okay, for example, you have a load P acting A away from the leftmost portion of your beam. Okay, we are talking about leftmost portion of your beam. If it is A away from the body and then you have a downward load of P, your shear equation, okay, your suffix for your shear equation will be negative P. And then from your moment equation is negative P times X minus A. Where, okay, as I said, X is any, okay, X is any value or any measurement, okay, it is a distance measured from your leftmost part of your beam until up to any point within your beam. Okay, So here, load P, your shear equation is negative P, and negative P, your moment equation will be negative P times x minus A. And for distributed load, W, okay, which is located, its beginning is located A, at a distance A away from the leftmost side of your beam. So you will have a shear equation of negative W times x minus A. And then you will have a moment equation of negative W times x minus A squared over 2. Okay? Okay. So you might ask, what if this load starts at the leftmost side of your beam? So if that is the case, your A will be 0. Okay? So if this P is located directly at the top of your at the leftmost side of your beam, automatically your equation will be, your A will be 0. Okay, so if this P acts directly at the here at the top, it will be, your moment equation will be negative P times x. And if your W started at the leftmost side of your beam, it will become negative Wx for your shear equation and negative Wx squared over 2 for your moment equation. Okay? And then if you have, okay, this is good for your uniformly rectangular load. So what about if it's a uniformly distributed triangular load? Okay? In increasing order. So if that is the case, you follow this formula. Okay? For your shear equation, it will be negative W times x minus A squared over 2L. And for your moment equation, you will have negative W times x minus A to the power of 3 over 6L. Okay? So if it is 2 degrees, okay, and it is linear, it is increasing, steadily increasing, okay, we are, this 2-degree curve, we are talking about the degree of curvature. Okay, when we say 2 degrees, we are talking about the equation of the curve, which can be represented as y is equal to ax squared. Okay, if that is the case, if this 2 degrees, your shear equation will become negative W times x minus A to the cube over 3L squared. And then if for moment equation, you will have negative W times x minus A to the 4th over 12L squared. Okay? So what about if it is n degrees? Okay? If this is an n degree curve and it starts at a distance A from the support. Okay? So there is no problem. If that is the case, you follow this formula. Negative W times x minus A to the power of n plus 1 over n plus 1, okay, quantity n plus 1 to the times L to the power of n. And then for your moment equation, it will be negative W times x minus A to the power of n plus 2 over n, quantity n plus 1 times quantity n plus 2 multiplied by L over to the power of n, where L here is the length. Okay, please take note that the L here is the length of your distributed load. Okay, so this general equation actually applies to triangular and 2-degree curve also. This is actually a general formula. If your curve has an n degree, okay, so your n here can be 1, okay, so your n here should be greater than or equal to 1. Okay. Okay. So do not worry, because as we go on with our examples, you will understand what I really mean in our discussions. Okay. So these formulas, you might not find it in our books. Okay. So I actually personally made this chart in order that my students could understand better our lessons about shear and moment diagrams, and they could easily construct it no matter how difficult the loadings of a beam may seem, okay? No matter how difficult the load, okay, the form of the load, they can solve it, okay, by using shear and moment equations, okay? So all these things um, can be used to construct your shear and moment equations, okay? So these loads, okay, for example, if your beam has loads, uh, point load and distributed load, this respectively, actually you can combine, okay, you can combine the shear equation P and W if P and W both exist in one beam, okay? So this can be superimposed, okay? So these formulas can be superimposed, in which if one or two of these one or two of these loadings exist on one beams, for example, just combine its shear equations in order um, to determine what is the shear and moment equation for that certain point or certain range of the beam, okay? So please, you may or you may not memorize this one, okay, for your own consumption, okay? So we know what is basic shear and moment equation depending on the setup of the loads. So today, okay, after this, okay, so we will be tackling about how to draw your shear and moment diagram, okay? Okay, we'll draw your shear and moment diagram depending on the shape of your loading. Okay, so may I erase this one? Okay, so let's start with the reactions. Okay, so let us say at the leftmost of your support, you have a point load. Let us say it has point load, a reaction of R. Okay, so if it has a reaction of R, okay, its shear equation, okay, it's the form, it's the shape of its shear will be like this, okay? You will draw the shear, the direction of your the stroke in your shear diagram as this, upward, okay? So since it is up, so it should be upward, okay? Stroke like that, okay? So if it is, let us say, a distributed reaction, okay, so this may happen when the platform in which the beam um, is lying, or the shape of its supports is quite wide, so you can assume it as a um, distributed loading, okay, distributed reaction. So if that is the case, your the shape or the stroke in your shear diagram will be like this, okay? So please remember, this is actually the stroke, okay, the direction of your stroke. So it will increase linearly upward, this increase directly upward. Okay, so what about loads or loadings? So if your loadings is like this, okay, let us start at point load. So if it is your loading, okay, let us say it is P. So if that is the case, the shape of your shear will be downward also, okay, that direction. you will draw it at that direction. Then, if it is a distributed load, let us say this is W. So, its shape, since it is downward, the shape of its stroke in shear and moment equation will be like this. Okay? The direction of your stroke is going there. Okay, sideways. Okay, so this is actually a 1-degree curve. Okay, when we say 1-degree curve, it can be represented as y is equal to ax. Okay, so therefore the power of your x is to the power of 1. Here you have no x, so your x is 0. So y is equal to x to the power of 0, or just simply y is equal to a. So x here is non-existing because it's a vertical line. Okay, what about if it is triangular load? If it's a triangular load, W, the stroke of its shear in the drawing of its stroke in your shear diagram will be 2 degrees like this. Okay, when you ask what is a 2-degree curve, it is represented by y is equal to ax squared. Okay, so meaning it has a power of 2. Okay, in contrary to this 1-degree curve which has power of 1. Okay, so you may ask, sir, this is not a curve, it is a slant line. Okay, so it's true, but in algebra, in higher mathematics, okay, so in our lesson, this is a 1-degree curve and this is a 2-degree curve. Okay, I know. So this is okay, this is a 1-degree curve and this is a 2-degree curve. Okay, and this is 0 degrees. Okay, a vertical line, whether you stroke it up, whether the direction is upward or downward, this is 0 degrees. Here it is 1 degrees. Okay, here, okay, so this W, since it is horizontal, it could be also 0 degrees, and here it is 1 degrees. Okay, so when your the shape of your loading or your reaction is at a certain degree curve, its shear drawing will be 1 step higher of that curve, will be 2 degrees. Okay, so what about if the loadings is this a 2-degree curve? Okay, so what is form of shear and moment? Okay, let us add moment. Okay, so here we know the loadings are relative to shear. What about moment? Okay, so may I erase this one? Okay, so for moment, it is actually 1 step higher. Okay, so if this is the shear, your moment will be like this. So this is 0 degrees, this is 1 degrees, stroke like that. And then for this moment, okay, it would be like this, be stroke like this. Okay, so this is actually a 2-degree curve and this is 1-degree curve, this is 0 degree. Okay, okay, so from your reaction or your loading, okay, you add 1 degree. Okay, starting from your loading. Okay, starting from your load diagram to shear, it will add 1 degree. Okay, so your 1 degree is like this, and your 2-degree curve will be okay like this. Okay, so this is a 1-degree curve increasing, and this is a 2-degree curve decreasing, increasing also. And when the loadings will decrease. So since this is 0 degrees for shear, your 1-degree curve will be like this. decreasing also. Okay, so this is a 1 degree curve. Your moment, you will be one step higher. Okay, so if this is your 1 degree, your 2 degree curve will be like this. Okay, and then for your moment, it will become 1 degree higher again. Okay, so this will be 3 degrees. Okay, so just, okay, have you seen the pattern? Okay, from your load diagram or reaction, from your load diagram, you just increase 1 degree, you will get the stroke for the shear. And for your shear, from your shear, you add 1 more degree and you will get the stroke of your moment. Okay, so this is the direction of how you stroke your drawing in your shear and moment diagram. For your loadings, which is can be, okay, can be represented by this curve. Let us say this is a 2 degree curve W. Your stroke, since it is increasing, since this is decreasing, so the stroke here, your curve is like this. So it is a 3 degree curve. For your moment, it will be a 4 degree curve. Okay, or your three. Okay, when we say 3rd degree curve, it is like y is equal to a to x cube. Okay, so in which it has a power of 3. Here, because it's downward, so your a might be, should be negative. Okay, also for this moment, its power, when it is represented by an equation, is it has a power of 4. Okay, so that's how it works. Okay, so we are talking about highest power. Your highest power here is 3, okay, x to the power of 3, and highest power for your moment is x to the power of 4. So what about if your loading is in n? Okay, let's say n degrees. So if that is the case, your shear will be n plus 1 degrees, and your moment will be in n plus 2 degrees. Okay, so this is the shape of the curve. But somehow, if it's the other way around, let us say a triangular load decreasing, so the shape of your curve will be reversed. It will be like this. Okay, so this is your W, and it is actually a 1 degree curve, so therefore it is a 2 degree curve, and here it will become a 3 degree curve for your moment. Also for your, if your loadings are 2 degrees and n degrees respectively, it will become the stroke for your, okay, how you stroke it in your shear diagram, it will be 3rd degree, and for your moment it will be 4th degree. If you're, okay, so please take note of the shape. It depends upon the shape of your loading. Okay, if it is n degrees, it will become n plus 1 degrees, okay, in shear, and for in your moment it will become n plus 2 degrees. Okay, just take note of the direction of how you stroke it in your shear and moment diagrams respectively. Okay, so this, okay, so, okay, so this is how you draw, okay, your shear and moment diagrams with respect to your reactions, okay, the reactions and loadings, external reactions and loadings. Okay, so we will understand better our lessons if we have for examples. Okay, so we will have our examples, series of examples on the next videos. Okay, so if you are interested to continue, you may continue on the next watching the next videos in in our lecture series. Okay, so thank you for your attention.